Hey everybody, Dr. Retzig back with you here. This is our second video for Math 406, and we're right at the outset where we're just figuring out what we even mean by the words inner product. So as you can see here, what we've got is we've got a vector space V, and it's got an additive identity in there, and then just got some objects U and V. This could be Fn, but it isn't necessarily Fn. This is just a big box of vectors. An inner product on a vector space is a function that takes pairs of vectors and spits out scalars. So it combines two vectors and turns them into a scalar. The notation is this angled bracket u comma v notation. And to be an inner product, it just has to satisfy a few properties. Okay. The first property is positivity. Positivity just means that anytime you inner product V with itself, it comes out bigger than or equal to 0. The second property is definiteness. Definiteness just says, hey, back there in property 1, if it comes out equal to 0, V must have been 0. So we can say that this way. V inner product V comes out to 0 if and only if V equals 0. The third property is called additivity in the first slot. That just means U plus V inner product with W is the same as U with W plus V with W, and that's for all U, V, and W in V. Homogeneity in the first slot just means you can factor things out. So lambda V against W is the same as lambda times the inner product of V with W. And that's true for all scalars, lambda, and for all V and W in the vector space. And finally, there's conjugate symmetry. Conjugate symmetry means inner product of U with V is the same as the conjugate of the inner product of V with U. So if you switch the order around, you pay with a conjugate. That's complex conjugation. So for example, the conjugate of the complex number 2 plus 3i is the complex number 2 minus 3i. And that's got to be true for all U and V in V. Now, you've read up through this definition, and these 5 properties are required so that whatever we end up calling an inner product reminds us of dot product way back from calc. So for example, you could be thinking of a somewhat exotic looking inner product in a somewhat exotic vector space. What if your vector space was, say, all polynomials up to degree 3 with real coefficients? So examples. Well, there's the 0 function, there's 2x plus 5, there's x cubed minus x, there's 5x squared. This is a big box full of polynomials, degree at most 3. We could define the inner product of polynomial f and polynomial g inside this box. So there's f, say, here's g. If you want to know what the inner product of those two polynomials is, we could declare it to be the integral from 0 to 1 of f of x times g of x dx. Certainly, this will spit out a number. That integral will come out to something. And you can check that the 5 properties are all true. Note that that 5th property, conjugate symmetry, it's not a big deal in this example because everything's real valued. So complex conjugation doesn't even do anything. And all the other examples are pretty evident. So this really does meet properties 1 through 5 of the definition of inner product. This meets 1 through 5 of definition of inner product. Okay, so inner products don't have to look like dot products. All they have to do is satisfy 1 through 5 of the definition. All right, now, those properties 1 through 5 in the definition of inner product, those actually purchase other properties of inner product. So your reading today is all about collecting those other sort of arithmetic properties that any inner product in any setting will have. So I thought we could maybe go over 1 or 2 of those properties. You guys can read about why the others are true. And that'll be it for making progress through, I think it's theorem 6.7 is your reading to get ready for Thursday. Okay, so let's start making a list of properties of inner products. Certainly they have the 5 properties in the definition, but those actually purchase still others. So this is properties of inner products. Now the first one we touched on in our class discussion today. If you define a map from your inner product space V, mapping into the scalars, by thinking of a certain vector in V as being fixed, so U is not going to change. The formula for the map is T of V simply comes out to whatever V's inner product with that fixed vector U is. So T just takes each input over here from the vector space V and computes its inner product with that specific vector U. That map is linear. And that's that first property in theorem 6.7. This is a linear mapping from V into the scalar field. And it's easy to see that it's linear because to be linear is simply to satisfy properties 3 and 4 in the definition of inner product. So if you have a working inner product, this map T that we've defined is automatically linear. Then as soon as you know that, once you know that T is linear, a bunch of other stuff follows. So for example, certainly, if you're interested in V inner product with 0, well, that's got to be 0. Because linear maps send 0 to 0. Now, actually, that wasn't put very well. Remember, in this mapping up here, T is taking inputs V and inserting them in the first slot. Down here, it looks like 0 is being inserted in the second slot. So maybe we should say something like this instead. We'll get rid of all this and rephrase like this. Then certainly 0, comma U comes out to 0 for any U in our vector space. That statement looks like T of 0 is equal to 0. And we know that's true for linear maps. So any linear map sends 0 to 0. So in any inner product space. If you do an inner product with 0 in the first entry, you get 0. But then, at that point, once you know inner products with 0 in the first entry come out to 0, then you can use property 5 to argue that inner products with 0 in the second entry also come out to 0. But then, by 5 of the definition of inner product, we know, sorry, that's the dog. We know that U, 0 is the inner product of 0, U conjugate, which is simply the conjugate of the number 0 by this statement, and the conjugate of the real number 0 is 0. So at this point we know if you inner product with 0 in either the first slot or in the second slot, the result will be 0. These are the first few properties of theorem 6.7. There are a couple others about whether you have additivity in the second slot and how homogeneity might work in the second slot. You guys should read those. The proofs of all of these elementary properties come from playing properties 1 through 5 of the definition off of one another. So at this point, we know that in an inner product space, you have certain nice properties. Inner products are abstract things that are meant to model dot product, and hopefully they'll be useful to us and lend additional structure to the vector spaces we're going to study. The first sense in which that's going to happen is your next reading assignment, which will be to get ready for Friday's class, concerning norms. All right, that's it for now. Make sure you read up through the proof of section 6.7 to be ready for class on Thursday, and I'll see you next time. Bye.